Hello everyone, my name is Riccardo Bortolomiotti and today I'm going to present HeadPrint, a work that I have done at the University of Twente while I was a PhD student, together with my colleagues and in collaboration with other institutions such as UCSB, University of Munster and Bitdefender. I'm sorry in advance for the poor quality of my microphone. Sorry. So HeadPrint is a system that tries to apply passive application fingerprinting for anomaly detection. At a high level, it works as follows. We have a security monitor that inspects the traffic of one or more machines. And from the traffic, it tries to identify and extract fingerprints from different applications that are generating the traffic from that machine. Once this training phase is finished, during testing or the detection phase, the security monitor keeps monitoring the network and then it tries to identify whether each message matches or not with one of the fingerprints that are known from the training phase. If no match is found, then the message is considered suspicious. And multiple suspicious messages may generate an alert later on. When we look at the literature of application fingerprinting techniques, we can see that most of them focus on identifying the presence of applications in the network. So for example, you want to know whether the employees are using WhatsApp in your network, you have the fingerprint of WhatsApp, and then you try to see whether there is traffic that is matching that fingerprint. Now in the setting of anomaly detection is slightly different, because you want to know whether there are unknown applications in your network. The most recent work that discusses this specific topic is Decanter. Unfortunately, Decanter has some limitations. The features it uses to generate fingerprints are few, handpicked, and overall they are not good in discriminating all the applications. For some applications, those features are not very well discriminating. So what happens is that you have a fingerprint of a specific application, you have traffic generated after you generated the fingerprint that Decanter is not able to match back to the original fingerprint. Therefore, it's considered unknown, and then on the long run it generates false alerts. A similar issue occurs when software is updated. If you have a browser that is being updated, some information in the network slightly changes, and then Decanter is not able to map correctly that updated messages to the original fingerprint. And therefore, this also contributes to false alerts. And our goal with this work was to have a fingerprinting technique that is more accurate and less error prone and tries to generate fewer false alerts, because it's important for security operators to spend their investigation time on alerts that worth investigating. So we want to reduce as much as we can the alert fatigue that operators may face from such systems. So the major contribution of this work is a novel fingerprinting technique. Instead of relying on some hand-picked fields, what we do is we analyze the network traffic, the network messages of each applications, and we infer from them what is relevant and it was not. That is one difference from Decanter. Plus, we also use header sequences, which is a different type of features that was also not used before. It's important also to say that HeadPrint works on HTTP, so it doesn't work on any protocol. At least we tested only on HTTP. This new technique, in our evaluation, outperformed Decanter in pretty much all the aspects we have evaluated. It's more accurate in identifying the applications over time, so it makes less errors. It's more resilient during application updates, and therefore, due to these two observations, it also generates fewer false alerts. The intuition of HeadPrint is that we can distinguish applications by looking at what values they use or they associate to each header, and what sequences of headers are being used in the network messages. The idea is that header values capture the application semantics, and header sequences captures the implementations of the application. Now we're going to dive a little bit more into the technical part of HeadPrint, and then we will do the evaluation, limitations, and conclusions. So fingerprint training works as follows. We collect the messages from a specific application, and then we create two models, one for the header values and one for the sequences. And the fingerprint is a tuple of these two models. We also have two similarity functions for each of these models, which allow us to compare a network messages with the model of a fingerprint. And the result is a score between 0 and 1. And the scores of both similarity functions is given as input to a decision function, which will determine whether these scores are high enough to determine a match or not. The header value entropy model works as follows. The goal is to determine what headers and their associated values are characteristic for an application. So first we collect from all the messages, and we group all the values that are associated with each header. You can imagine it as a dictionary where you have the headers as keys, and as values you have this multi-set of as values associated with the key, you have this multi-set of header values. And now we want to determine which of these headers and their values are characteristic for an application. And the idea is that the more stable and predictable these values are, the more characteristics are for an application. So in the future, if I really see that value on the network, if it's predictable, then it's more likely to be that application that is communicating. That's the overall idea behind it. And how can we distinguish whether a set of values is predictable or not is by using entropy. Values, so the multiset with high entropy is highly unpredictable. It means that we will have a new value every message, and that doesn't help us to recognize an application. If the entropy is low, it means that we will probably see again the same value over time, and that will help us to re-identify the application. So, said that, headers and values with high entropy are discarded, the one with low entropy are kept into the model. And this is done according to a threshold alpha that we set. Details are in the paper. We also have a similarity function that allows us to compute how similar is the content of a message with the model. And this is essentially a similarity function for categorical data. The idea is to see how many of the headers and their values that are in the message are also present in the model of the fingerprint. We then divide the total by the total number of headers in the message, and we have a score between 0 and 1. Of course, the closer the score is to 1, the more similar it is to the content of the model. For the header sequence model, the model is just a set of all the header sequences observed in the message collection for that application that was used during training. And the similarity function works as follows. We extract the sequence from the message, and then we compute the longest common subsequence similarity function between that sequence and each sequence in the sequence model. The highest value is then reported as the output of the similarity function. The longest common subsequence was discussed by Daniel Backlund, and we use that work as a reference for this. We discuss more into the paper on why we chose such a function. Once we have obtained both scores, we give them to a decision function. The decision function will decide whether these scores are a match or not. In these pictures, you can see an example. This is a fingerprint for Firefox, and on the y-axis we have the sequence similarity score and the value similarity score on the x-axis. And you can see that when we try to match another applications with the fingerprint of Firefox, we can see from the green crosses that the scores are pretty low and stays pretty much on the left bottom side of the graph, while when we are trying to match the Firefox messages, we can see that they are on the top right corner. And the decision function, their task is to determine the boundaries on when consider something to be a match or not. And we will use, in the evaluation of our work, we will use some machine learning based functions and some simple threshold based functions. We used HeadPrint in anomaly detection, as we have said since the beginning. We trained. The training was as follows. We collected messages using a similar user agent that was assigned for by an indication that were generated probably by the same application, and we generated the models with the collected data. We have some also sort of convergence mechanism to optimize the training, and that's also discussed in the paper. And then during the testing, we verify whether each message generated by the host matches or not with one of the fingerprints. If no match is found, the message is considered suspicious, and then the alert is triggered once we have enough messages towards the same destination. We have more details of this in the paper. The idea is to, if the amount of data that is being sent towards a specific destination is high enough, according to a threshold, then we trigger. Evaluation. Okay, let's talk about the evaluation. We used, first of all, we tested the HeadPrint using different decision functions. As I said, a threshold-based, different threshold-based functions, and machine learning-based. And we tested our solution and the counter as well on a data set collected over a little more than a month. We had almost 4 million HTTP requests over 300 hosts, and roughly we use 400,000 requests for training and 3.4 for testing, 3.4 million for testing. This graph, before we go to see the detection numbers or other classification performance numbers, I want to show you this heat map, which describes the entropy values for a specific set of headers that you can see from the columns. And in the rows you can see different applications, and these pictures shows you how each application uses in a different way specific headers. So you can see from the browsers that the entropy of cookie values, referrer and host have a very high entropy. They change all the time depending on the website you are connecting to. So it's very hard to use those fields to predict whether you're using Chrome or Firefox or something else. On the other hand, the same fields tells you more about an application. In the case of Spotify, the host Spotify connects to is rather stable compared with the browsers. So in that sense, for that application, makes more sense to include the host while not for other applications. So that was just a quick view on the entropy and the model, the header value model. Now in this slide we can see the overall performance in fingerprinting accuracy. So in this experiment, what we wanted to do was to see was the following. Given a message, we want to match it against one of the fingerprints, and we want to see whether the fingerprint that it matched with is the fingerprint representing the original application. And we did this for the whole dataset, of course, and we can see the three classification performance metrics: precision, recall, accuracy. And what you can see from the table is that Decanter performs significantly worse than HeadPrint, no matter what is the decision functions being used. And this has to do still with the different type of features that are being used in the fingerprinting. And this is highlighted in the recall, and the recall is exactly what we discussed at the beginning, that we have a fingerprint of an existing applications, but we cannot match whether this new message, so that basically low recall means that we have the fingerprint of the application and the counter is not able to correctly associate the messages of that application to the fingerprint. The precision is quite high for all the decision functions, also for decanter. Actually, decanter is slightly higher. What that means is that decanter makes fewer mistakes in assigning the message to the correct fingerprint. So in some cases, HeadPrint finds a match, but it assigns this to another fingerprint. In the case of low recall, it simply does not find any match. How HeadPrint survives application updates. Okay, so this graph shows you why HeadPrint can survive application updates, meaning that it still can match the messages of an updated applications to the original fingerprint. We have again a fingerprint from Firefox, and we have three type of dots. The blue dots are the Firefox messages of the original, of the same version of the fingerprint, let's say. And as you can see, they are on the top right. And we have the red dots, which are the messages from an updated version of Firefox. And as you can see, it's still in the top right, but the value similarity has decreased. And this has to do, for example, when you update, your string of the user agent changes. So, of course, the value similarity also then is reduced because it doesn't match with the one in the original fingerprint. However, if you see, the sequence similarity is pretty much the same. It doesn't drop. It's some sort of it's an orthogonal feature that is not affected by software updates, and it helps keeping the detection, the correct detection of the application. If we look at the other applications, also in this case, the majority do not correctly match with the fingerprint. So that's how HeadPrint can deal with the application updates. The last analysis that we have done some slightly more analysis in the paper, but for the presentation, this is the last analysis I'm going to discuss. We did some manual evaluation on the alerts generated by Decanter and HeadPrint. One thing we did was to analyze our network traffic through the indicators of using the threat intelligence by a third party. And we identified a set of hosts that trigger some of the indicators from this third party. And out of these hosts, which the number was around 10 or 13, 3 of these hosts were also included into Decanter, and 2 of these hosts were included in the HeadPrint alerts. We also evaluated the other alerts, and then we saw that Decanter showed 5 hosts that were doing suspicious activity and aborted the next investigation, and HeadPrint found 3. So although Decanter found more suspicious activities in the network, we can see on the table on the right that Decanter generates a significantly larger amount of alerts, which means also a significantly larger effort that an operator should do in order to evaluate the alerts, because many of these are, of course, false positives. So overall, you can see that by increasing the threshold, all the alerts, so the HeadPrint can decrease the number of alerts being triggered, so it can slightly fine-tune the alerts amount that you send to the operator, while for Decanter this is not the case. The threshold does not really matter that much. Limitations of HeadPrint. HeadPrint, of course, cannot work when the connection is encrypted, so in case of HTTPS, HeadPrint cannot be used unless in the network we have a man-in-the-middle TLS box that can decrypt the traffic, and it can be analyzed there. Regarding evasion, HeadPrint can also be evaded in case the attacker tries to do a mimicry attack and tries to emulate the network messages or copycat the network messages generated by the applications installed on the victim itself. Although this is certainly doable, it also requires malware samples to evolve, in a sense that we are not really aware. Definitely this is not common practice between malware, so we're not aware of samples that use this technique, but it is possible. In conclusion, we can say that inferring relevant headers from the traffic of each specific application works better than picking few features a priori, independently from how the application uses the protocol. That's shown by the differences in performance by Decanter and HeadPrint. The other sequences help to tolerate software updates. Software updates do not seem to affect much header sequences as much they affect the content, so it's a good features that can be used to keep accuracy high despite some minor changes occurs in the network messages of updated software. And overall, HeadPrint is a more accurate solution than Decanter, and is a step forward towards a more practical solution. And that's about it. So if you have any question, please feel free to contact me, and we'll be happy to answer you. Thank you.